All right, so page 27. This is a comparison between integral rules, mostly rational expressions. So we're just going to go through each of them, and the key is on the back, page 28. If you want to work this out on a separate sheet, just give yourself more room. Okay. Okay, so let's start off with this one here. Example 1. 1A. So if there's only one term in the denominator, we don't really care about what the degrees are. Okay, it could be higher, it could be lower. We're just going to go ahead and start splitting up. Right? There's no need for us to hold on to one expression if we can split this up into 3 separate, easier expressions. Okay, so anytime there's one term, I'm always going to look for a way to separate into individual smaller problems. Okay, and then within each fraction, now we're going to try to clean up and see what rules apply for each of these problems here. Here I can reduce x to the 4th, and x to the 4th can cancel out. I'm left with 1/2. 5 over 2x. Plus 1 over 2x to the 4th. Okay, I'm going to get every term ready for whatever rule I want to apply. So this is just going to be 1/2 minus, and really you don't have to do this, but I just want to kind of stress the fact that these are really 3 separate problems, right? So you could really do 3 separate definite integrals. You don't have to, but visually, I'd like to kind of stress how these are really 3 separate problems. And this, I have to bring the x up to the top. So I don't want to do natural log for this one, right? I want to do power rule. Okay. Power rule, natural log, power rule. Okay. 1b, let's try this one as well. This is also has one term. It may not be power rule, but we still want to separate into individual terms and see what we can do for each term individually. Morning. Okay, let's clean up each individual term. So if I have common bases, I can subtract exponents. 4x minus 3x is 1x. 2x minus 3x is negative 1x. I do want to bring both base e to the numerator because I don't have a rule for e to the x in the denominator. I only have rules for e to the x in the numerator. So that's why I'm forcing that e to the x, negative x, or e to the x from the denominator up, or I can just subtract 2x minus 3x, gets negative 1x. Either way, I have to make sure that these are up to the numerator. And we're on page 27 of the 6.3 packet. Now, this is just a clean integral rule, but this is a little bit of u substitution. You don't have to go through u substitution, just understand that there's a negative 1 that's going to come out of it. But if you wanted to, you can still go through u substitution here. So basically, that negative is going to force this sign to change. So that's going to leave me with 2/3 e to the x plus 1/6 e to the negative x plus c. Right, the integral of e to the u is just e to the u. Just have to keep track of the coefficients here. Okay, all right, let's look at 2b or 2a, the second row here. Now these are terms where the degree is 1 higher in the denominator than the numerator. Okay. Mm-hmm. 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 Okay, let's try 2a here. So if we look at this problem to begin with, we notice that there's too many terms in the denominator. We always want to try to see, can we just rely on power rule expansion? But there's 2 terms, so that option is out. We can't expand. So the next step is, well, what about u substitution? We can try to target the denominator, and the denominator has degree that's 1 higher than the numerator. That should be a good fit, right? Anytime a degree is off by 1, we know that the derivative will work to work down to that degree that we ultimately want to cancel out. So we're going to target the denominator as our u value. Make our substitutions here. Okay, got the x's to go away. Push the 5/14 out in front. This is 1/u to the first power, so we know that's natural log. Okay, let's look at 2b. Can't expand too many terms in the denominator, but we see that, well, if we go to u substitution, looks like that u value is favorable, right? This degree is 1 higher than the numerator. Anytime there is a staggered degree relationship, we know that u substitution should handle things pretty nicely for us. So let me rewrite that denominator, though. I'm always looking for a set of parentheses, especially if there's a messiness like this problem. Okay, 5th root, what does that mean? Parentheses to the what power? 1/5. Okay. Okay, yeah, I always like to, if I'm doing u substitution, I always like to create a set of parentheses just to make things more clear. All right, when we find this derivative, it should handle that x squared nicely for us. All right, let's make our substitutions here. Just like what we wanted the x's to go away, and they do. X squared, x squared. So we're on page 27 in the 6.3 packet. Now, there's a variable in the denominator, but what rule do we use for this u to the 1/5? Okay. Can we use natural log like the previous problem? Okay, why not? Yeah, that exponent is other than 1, so I have to use what to do this rule?
It's 1/ln(a) times a to the.
We only do that 1/ln(a) if it's like a exponential function, like 3 to the x or 4 to the x, right? This is a variable raised to a constant. So yes, and use power rule, right? So this is a power rule problem. But this u is out of place, right? So we have to push this u up to the top. Okay, go through power rule. Add 1 to the exponent, right? So u to the 4/5 over 4/5 plus c. We can get that 4/5 to be 5/4 in the numerator. (10 over 36), but we can let that reduce down to 5 over 18. And remember, anytime you involve u substitution, your u is only a temporary variable, right? If when we get to the end, we should always, once we are finished with our calculus, we always have to make sure we bring back our original variable. Okay, number 3. Okay, let's go down our checklist, right? The first option is, can we expand? There's already too many terms in the denominator. We can't split up like we can if it was just 4x minus 5 over x, then we can split up into separate fractions. But at x minus 3 prevents us from doing it. If we look at u substitution, if we let the u value be either the denominator or the numerator, the degree is not high enough for us to get that to occur. Okay. So you see that the degree is not favorable for u substitution, but the denominator are the same degree as the numerator. So if either the numerator is higher or they're the same, that's a potential for synthetic division or long division. But long division would be if the degree was like x squared, but this x minus 3 is good for synthetic division. Okay. So we're going to go through synthetic division here. Yes. Oh, sorry. Thanks. Okay, synthetic division. Again, synthetic division does not solve the problem for us. It only produces a form for this problem so that we can identify integral rules that are easier to identify. Yes. Right. There's no long division. So I'll adjust the second part, and I'll talk about situations that needs long division, but we won't have it on the test. Okay. So x minus 5. We always, to do synthetic division, we also have to take the solution from this x minus 5. We also have to take the opposite sign of what we see here. And now we have to list out the factors, or list out the coefficients. 4 represents the linear, and -3 represents the constant. Okay, so we're just going to drag that 4 down below. Once it's outside the box, we multiply with the number outside. 5 times 4 is 20. Add. So that's it. So this is, if the last number in your columns is not a 0, that means this is called the remainder. Remember, every degree drops by 1, so this is 4x to begin with. this is going to drop down to a constant. So this is 4 plus, and then we know 17 is a remainder, so we have to write the remainder over your divisor. So now we have a problem that is the same as the original problem, but it just makes it easier calculus-wise to apply rules that's available to us. Okay, any questions so far? All right, so 4, how do we handle 4? What rule do we use there? We don't have to go through your substitution if it's as simple as this. What's the integral of 4? 4x, yeah. So a constant just rises up to first degree. Now this, we can go through u substitution. But it's relatively easy. You don't have to go through a full u substitution because your u value isn't going to produce anything more than the 1. So this is just going to end up being what rule here? If you want, I mean, if you want to just always go through u substitution, you can. It ends up being 1 over u du, right? If you push that 17 out in front, replace dx minus 5 with u, replace dx with u, this ends up being natural log. So 4 becomes 4x. 17, 1 over u becomes 17 natural log absolute value of u. And then I'm going to replace the u back in terms of my original variable, x minus 5. Okay, 3b. Okay, I'm going to adjust this. Well, any questions with 3a? Okay. 3b, I'm going to make an adjustment here, but I want to talk about this for a moment. Okay. This, too many terms in the denominator. This would be perfect to split up if it was just x squared. There's too many terms in the denominator. U substitution is not going to be a good fit because either my denominator or numerator is not going to be high enough degree, or the gap is too big, right? And also, this is not arc trig. We only do arc trig if there's a gap with the denominator being the higher degree. If the numerator has a higher degree and there's a gap, then we have to consider either long division or synthetic division. Now, as this stands, we will not be able to do this with synthetic division because this degree is too high. Okay, but I won't be putting long division on the test, but I just want to show you that if you see this problem in the future, we do AP exam review, this is a long division problem. I'm going to make the adjustment though. I'm going to take that 2 out. I'll just make it x plus 2. So now there's a sizable gap. The numerator is higher. This is going to be a synthetic division problem. Okay, so I'll take out that x squared, just make it x plus 2. So always take the opposite sign. And now I'm going to list out the coefficients. Okay, 1 is for the x to the 4th. Now something that we have to make an adjustment for. What adjustment do you see that has to be made here? You notice anything about those exponents?
There's no 3 and 2.
There's no 3 and 2. You have to have a placeholder for every degree that is skipped over. So the first column is for x to the 4th. We need a second column for x to the 3rd, x squared, x to the 1st power, and the constant. So if you don't see anything, then think of it as 0. There's 0x cubed, there's 0x squared. 1 for the x, and -4 being the constant. Okay, any questions here? All right, so we take the first term down below the line, multiply with the outside number, add inside the box, multiply, add, multiply, add, multiply, and add. And double check here. Okay. Now, what's the degree of this first term? All right, so if I started with x to the 4th, okay, I'm always going to drop by 1 degree. So every term is going to just fall by 1 degree after that. So x squared, x, constant, and then finally the remainder. We can also do this using long division, but I think we prefer synthetic division. It is a little gimmicky because we have to kind of keep track of all these specific rules, but it goes a lot faster. Okay, any questions so far? We haven't solved the problem. We just created a simpler problem to work than this. No, we haven't done any calculus here yet. So now every term is nicely set up for power rule, except for the last term. The last term is u substitution, but it's going to be a natural log one. So we can really think of this as tan integral of 1 over u du. Okay, power rule. Leave it like this, or you can maybe do a little bit of cleanup if you like. Okay, number 4. Okay, 4a. Now take a look at 4a here. Too many terms in the denominator, right? We can't expand. U substitution is not favorable because the degree is 2, but the degree here is 0. That there's more than a 1 degree gap between numerator and denominator. But you see how it's different from the previous problem? You see how both 3b and 4a, they both have gaps, but the gaps is different for between numerator and denominator here. Here, the degree is higher in the numerator, right? But here, the degree is higher in the denominator. So both of these have gaps, but if there's a sizable gap with the numerator being the higher degree, then it's synthetic division. If there's a sizable gap with the denominator being the higher degree, then it's going to be arc trig. Okay, you see that distinction here? And also you see that compared to 2a, right? There's a degree, the higher degrees in the denominator, but this is only a 1 degree difference. So we always want to explore u substitution. But here, that degree is too big, right? X squared versus x to the 0 power. So we have to consider arc trig. Okay, so if we are considering arc trig, there's only 3 options, right? There's arc sine, there's arc tangent, there's arc secant. Both arc sine and arc secant have square roots, so we don't see any square roots, so we know we can't fall into that category. This will have to be an arc tangent. However, this trinomial, the standard form, is not quite set up for us to pull the a and u value. We have to go through an intermediate step, and that intermediate step is completing the square. Okay, so we have to step to the side and focus on trying to get that trinomial to be to give us a form that's easier to work with. Okay, so we're always going to introduce 2 spaces, blank spaces, into the problem. One is going to come after the first 2 terms. Another one is going to come after the last term. The first term will be positive and the second will be negative. Okay, what goes in those spaces? What's the formula?
B over 2 squared.
B over 2 squared. Okay. All right, what's our b value?
Oh. 16.
Our b value is just the 8,
Oh.
right? -8. Okay. So we have, but yeah, you're right. Eventually, it's going to turn to that. So we have 8. I'm going to leave the negative out because I know it's going to become positive anyways. So 4 squared is 16. Yeah. So as long as you know how to get there. So, okay. So 16 goes in both spaces, a positive 16 and a negative 16. Sorry, I did not, this problem I messed up on. Okay, let's just make a slight adjustment. If you guys can change this 4 to a 24, plus 24, because we should never be getting a negative after this. So yeah, so just slight adjustment here. We don't have to change much. Our steps can still stay the same. It's just this number needs to be, we can't end up with a minus sign in between. Okay, so sorry. Okay. Change the original problem to be x squared minus 8x plus 24. And also I messed up on the key as well. Okay, everybody okay? All right, so this should be able to factor nicely. What multiplies to be 16 adds it to be -8.
-4.
Yeah, -4 and -4, right? Yeah, so we should always be looking for duplicates, right? That's the whole purpose is this should factor nicely so that we get duplicates. So -4 and -4, right? Multiplies to be 16, adds it to be -8. Okay, which we know we can clean up even more, make it x minus 4 squared. That's ultimately what we're looking for. We want that u to be inside a set of parentheses with a squared outside. Okay, how about the last 2 constants here? What does that combine to be? Plus what? 8. Okay. Okay, so we're going to reset. Now we have a more straightforward problem to work with. This is beginning to look like our a squared and u squared. I do have the a and u flip-flop, but and just know that your u has the variable and then your a has the constant. There's still one adjustment we have to make. What needs to happen with that 8? Yeah, we have to get both sets of parentheses to show up and fill those in, right? So the x minus 4 is set, but this 8 is not quite showing us the true a value. We want to fit it into a set of parentheses without changing the value, so I have to take the square root of 8. You can always double check, right? Root 8 squared does end up being 8. We haven't changed the problem, we just rearranged it in a way that makes it easier for us to pull the a and u value. Okay, a value is root 8. U value is x minus 4. We find the derivative to make a substitution for the dx. Okay. Replace everything in terms of a and u. Let's make it match the rule that we want to use. No coefficients to keep track of. So now we're jumping directly into our rule here. So 1 over a, our a is root 8. Our tangent of u over a no need to rationalize the denominator. You can leave your denominator with a radical, that's fine. Okay, last one here. Integral of 5x over square root of 1 minus x to the 4th. U substitution, expansion is out, too many terms in the denominator. U substitution is not a good fit, right? Our u value is x to the 4th. Our derivative is not going to handle that x. And there's a sizable gap now between the denominator and numerator. Denominator has a higher power. It's more than, that gap is more than 1. So we have to consider arc trig. The square root, we know it's either arc sine or arc secant, but the first term is a constant, so arc sine will be a better fit for this one, okay? Arc sine is the only one without the 1 over a in front. There's only 2 terms here, so we can jump directly into creating sets of parentheses. There's no need to complete the square. Okay, so let's fit this into the problem without changing the overall value. What can I put inside the first set of parentheses? Just a what? 1. Okay, 1 squared is the same thing as 1. What can I put inside a second set of parentheses? X squared. So x squared squared is the same thing as x to the 4th. We just made it easier for us to identify the a and the u value. Okay. It's nice to see that 2x there because we know that 2x is going to handle that 5x up top. Convert everything in terms of a and u, and we'll hope that the x will just go away when we make that substitution. We got the x to go away. That's a good sign. What can we do next? Put that 5 and 2 outside, right? If you look, perfect match with the rule that we want to use. We can now jump into arcsine. 5 stays. U over A. Okay. Any questions?